coming. It's my pleasure to be here today to give a presentation on material characterization kit that we have developed at our company, Swiss. My name is MCK. Founders of the company representing. So just a brief introduction. Our company is a spin-off from the Swiss Technology Institute in Lausanne, Switzerland. Our specialty are millimeter-wave and terahertz passive components, so waveguides, antennas, logic systems, and assemblies of those. We are primarily working in the field of testing measurements, telecom, and spectroscopy applications. So we have some reference customers. We have good collaborations with both Keysight and THz, especially in material measurements application that I will show today. And we are also spanning out into, as I said, telecom applications and some space compatible components. So just to give you a brief overview of the different things that we do, we have one product line which comprises so-called corrugated waveguides. These are waveguides with geometry that is different from the traditional rectangular waveguides that we are used to utilize lower frequencies. The reason why we have this product portfolio is because these corrugated waveguides have extremely low losses, and this is of interest when moving to millimeter wave or terahertz. The second product line is based on a new manufacturing technology that we have developed that is based on a combination of 3D printing and metallization of components. So we produce components, plastic components with 3D printing with high accuracies, which we then plate with RF functional coatings in order to obtain waveguiding structures with interesting properties, be it in terms of weight, cost, lead times, or complexity that is achievable with this new manufacturing technology. And the last product that we have recently launched on the market, and which is going to be the subject for this presentation, is our material characterization kit. This is an application product where, by combination of hardware and software, we offer a solution for rapid and accurate material characterization and millimeter wave and terahertz. So why do we want to do the electric spectroscopy? We want to do it because we want to determine how much energy is stored in the material when it is exposed to these millimeter wave and terahertz, and how much energy is lost in such a material when exposed to these frequencies. And ideally, one wants to apply this measurement methodology to all the materials that might be exposed to those frequencies in the different applications that we encounter. So solids, liquids, emulsions, polymers, foams, and biological tissues. So when you do permittivity measurements with electric spectroscopy on materials, depending on the wavelength at which you operate, you are interacting with different mechanisms in the cell. And for the people coming from lower frequencies, some microwaves, and moving up, we often have permittivity values that vary very little over frequency, so that the dielectric constant is actually constant over frequency. But when we reach the millimeter wave and terahertz range, we start to enter into a regime where we see some atomic effects, and where this dielectric constant is no longer constant, and thus where spectroscopy becomes interesting. So this type of spectroscopy has applications in semiconductor industry to characterize materials that are used to fabricate semiconductor devices, automotive and radar industry, obviously to know how these radars will interact with the materials that they will encounter in the application space. Ceramic sintering. There are a lot of processes now that use these microwaves and millimeter waves for manufacturing steps in ceramic industry, telecom applications, microwave chemistry, and a field that is growing in the last years is microwave aquametry. So when you reach the millimeter wave and terahertz range, you start having much higher absorption of water, and you can use this feature to do accurate water content measurements. This is particularly an interest in applications like pharma industry, where throughout the manufacturing process of medicine, for instance. You have different powders that need to be mixed and to eventually smash a pill out of them. And throughout these processes, the knowledge of the water content is of importance. Same thing for paper industry. Depending on the water content of paper, you have to regulate how much ink you put into the paper to print. And these are all things that can take advantage of dielectric spectroscopy at these millimeter waves. So there are many solutions on the market to do those kind of measurements. Traditionally, people use so-called free space measurements or rectangular waveguide-based measurements. But when reaching millimeter wave and terahertz, these techniques become increasingly challenging to implement and to implement reliably and accurately. So what we propose is a new device, which we call material characterization kit, which enables real-time fast measurements with a calibration procedure, a simplified setup, and a solution. So for each frequency band at which you can do measurements, we produce one of those kits. And the objective of this kit is to minimize sample preparation. So we do not require customers to cut their samples into particular shapes to enable the measurement. And the measurements, traditional measurement setup comprises a vector network analyzer with some frequency extension modules to bring up the measurement capability to these millimeter waves and terahertz. And then the test fixture to do the measurements. There's a calibration standard provided with the fixture. And we also provide a software that runs the measurement and does the data analysis. So from a hardware point of view, the fixture is based on the corrugated waveguides that I introduced previously. These corrugated waveguides are hollow cylindrical waveguides with dimensions that are bigger than the wavelength, so they are so-called overmoded waveguides. And these waveguides have the interesting property that they propagate a beam that is very close to being a Gaussian free space beam, but that beam is going to stay collimated throughout the propagation inside the waveguide, which puts us in a situation where we have a nice plane phase front at each position of that waveguide. The second interesting property of such a waveguide is that if you place in a gap along a transmission line of such a corrugated waveguide, providing that that gap has a sufficiently small size, which is on the order of the diameter of the waveguide, so a few millimeters in our case, the beam will simply fly through that gap with minimal reflection or loss while flying through that gap. And it's that very property that we use to calibrate our device and to place the samples that we want to study with our device. So the device that you see here has a rectangular waveguide connector on both ends. After that connector, we have a conversion to the corrugated waveguide. And you see in the middle, we have the gap for the sample with a micrometric screw to open or close that gap. So schematically, the measurement setup looks as follows. You see the two gray boxes on both ends of the image are the VNA frequency extension modules. Then the two triangles are a schematic representation of the conversion from the rectangular waveguide to the corrugated waveguide. Then we have some stretch of corrugated waveguide, the sample that is clamped in an interface between two corrugated waveguides, and then symmetrically the same on the other end. So the calibration procedure that we use is fairly simple. We start by removing the sample from the transmission line, closing the gap and measuring it through. Then we insert a metallic mirror in the position of the sample, and we measure short. And that's our calibration. Then we insert the sample to do the measurement, and while measuring the sample, we use time gating. The time gating is used to avoid having pollution of your measurements by multiple reflections inside the system that are not generated by the sample itself. And we use S21 and S11 parameters to then extract permittivity from the samples. The samples that we can measure, the aim of the device is not to require any sample preparation, so there's no limitation on the lateral size of the sample that can be inserted into the device. The thicknesses of the samples vary from 5 millimeters to about 18 millimeters, depending on the frequency frequency at which we operate. So the higher frequency we go, the thinner the samples have to be. The spot size under investigation is on the order of 3 to 11 millimeters, again, depending on the frequency at which you operate. And for some applications, it's of interest to build sample holders, for instance, to hold very fragile, very thin samples. So we do supply sample holders for those. And we are also in the process of developing custom sample holders for more complicated samples like powders, foams, or liquids. One important element of the setup is the software. So there are several solutions for that. The first solution is to use the readily available Keysight material measurement software, which is now being made compatible with our test fixture. Alternatively, we also supply our own software. This software configures the DNA, runs the calibration, acquires the data, saves the data, plots the data, and does data analysis to extract permittivity from the S-parameter measurements that are being made. So first example of the system. This is, by the way, the system that is currently on live demo on the Amtex booth, which I'm happy to invite you to join for a demo after this presentation if you're interested. So it's a WR1.5 measurement setup between 500 and 750 gigahertz. And again, we use a vector network analyzer, frequency extension modules, and the material measurements fixture itself. And the demo that we have here is in collaboration with Keysight Technologies and Virginia Daggers, who support the demo with their part of the hardware. So, first example of a measurement, simple material, sapphire, about a millimeter thick. So what you see on the left-hand side of the slide is the magnitude measurement for both S11 and S21, so reflection and transmission through the sample. And on the right-hand side, the corresponding phase measurement. What we see is the measurement data, so the blue and the red curves, but we also see a third curve, which we call best fit. The best fit is, in this case, the first data analysis model that we implement in our software. This is a fairly simple model where we assume a constant permittivity of the material over the frequency band. So constant epsilon and constant tan delta over the frequency band. And under that assumption, we try to find the best fit to the data. And we can see here that we have very good agreement between the fitted line and the measured line. So for this material, we have a good data analysis with this model, and we see that we can measure epsilon r of 11.33 and tan delta of about 10 to the minus 3. A second example of this approach with some fused silica sample, again a millimeter thick. We see magnitude and phase measurements of reflection and transmission, along with the simple constant epsilon and constant tan delta permittivity model. For some samples, this simple model no longer works because, interestingly, these samples have frequency dependence of their permittivity, so non-constant epsilon and non-constant tan delta. One example of this is a rather exotic material that we call yttrium-doped zirconium oxide. It's a very hard ceramic. When measuring this material, well, first of all, we see it's a very high permittivity material. It has an epsilon on the order of 33. But it also has frequency dependence in its permittivity characteristics. So we see that we have an epsilon and a tan delta that increases with frequency. And to achieve these results, we use a second model in our software, which for each frequency point will take the measured S-parameter data and compute the according permittivity. Second example of this concept is a material, a ceramic material from a company called Schott, where we see that we have a very strong frequency dependence of the loss tangent of the material that increases with frequency. So I've shown now 4 measurement examples where we have a simple dielectric material that we want to characterize in terms of permittivity. But the fixture can also be used to do more exotic measurements. One example of those is our Swiss Technology Institute, a laboratory working on spin dynamics, uses our device. and recently made a measurement on multiferroic materials. So these are magnetic materials that express a spontaneous magnetic resonance at a given frequency. And that resonance frequency depends on temperature. So you can compute that for this material, so it's EIFeO3, you have a theoretical double resonance around 550 gigahertz, which by inserting the material in our measurements fixture, we were able to measure with a simple transmission measurement. So if you can appreciate on the magnitude scale of this measurement, you see that we are making full use of the dynamic range of the vector network analyzer. This is a thin stripe of about 2 millimeter thick of this material, which experiences very high loss of the signal in transmission mode. But despite that very high loss, we are able to resolve the two spectroscopic resonant peaks. And what we also were able to resolve is that these resonances have frequency dependence owing to the structure of the material itself. So by heating up the sample, we are able to move those resonances in frequency, which validates that we are actually looking at this feature. So this is just an appetizer, but it shows that the concept can be used to do spin dynamics, spintronics, and magnetic resonance measurements in general. A second example of a system, this is a system at a lower frequency band, the WR5.1 band, so between 140 and 220 gigahertz. Again, same system architecture, a VNA frequency extender, VNA with frequency extension modules and an MCK. At this frequency, we again have materials that have a constant behavior in terms of frequency, dependence of permittivity. So here we have silicon nitride, so Si3 and 4, about 0.5 millimeter thick, where we are able to resolve again the strong resonance features that we see inside those materials, and where the constant epsilon model gives good agreement with the measurement. I don't know if you remember a few slides before we showed yttrium doped zirconium oxide between 500 and 750 gigahertz, and we saw that for that material we had a strong frequency dependence of permittivity. Now if we move down in frequency, we suddenly realize that that material no longer has a frequency dependence on its permittivity, which shows that at this millimeter wave and terahertz range, there is really a transition from a rather constant permittivity behavior as a function of frequency to a strong frequency dependence of permittivity. So typically now at 140 to 220 gigahertz, we're below the threshold for this material, where we have a constant permittivity behavior. For some materials, though, it is not entirely constant. In this example, we show a piece of endode silicon, so a piece of wafer, essentially, cut off 0.5 millimeter thick, for which we measure the S parameters. And we see that for this material, the constant permittivity model, again, shows some problems, so we have to move to the frequency-dependent permittivity model. And we see that actually, surprisingly, for this material, there is a slight decrease of the loss tangent as a function of frequency. Another ceramic material of another manufacturer, where again we see a frequency dependence of the permittivity. So in this case, an increasing loss tangent as a function of frequency. At these lower frequencies, there are also some interesting applications. This is a result that was measured in collaboration with a company in Finland called Premix. Premix is specialized in dielectrically engineered materials. So they supply on demand dielectric materials with custom permittivities. So it's a plastic matrix that's doped, and depending on the level of doping that they apply, they are able to reach different dielectric constants. So one of the materials they commercialize is called Prepern 225. It's supposed to